Assalamualaikum and good day to everyone. Today we continue to our new topic on reduction of a simple distributed loading. The objective of the lecture today are number one, you should be able to determine what is a single resultant force. Number two, you should be able to determine what is the magnitude of the resultant force. Number three, you should be able to determine the location of the resultant force. Now we study what is the distributed loading. So, based on this figure, we have beam here, and then we have distributed load. So, in many situations, a surface of a body is subjected to a distributed load. So, this is the distributed load. So, what is the distributed load? Such force caused by wind, fluid, or the weight of item of the body surface. So, usually distributed loads are defined by using function W is equal to Ws. Okay, this is the intensity. So the intensity is measured in Newton per meter. And then the external effect caused by a coplanar distributed load acting on body can represent by a single resultant force. This one. So it can be represented by the dF. Here, dF single resultant force means that from this UDL is become single resultant force FR. And then how to determine the magnitude? The magnitude of the resultant force is equal to the total area under the distributed loading diagram. And then how to determine the location? The locations of the resultant force is given by the fact that its line of action passes through the centroid of the geometric center. So let's say this beam is L. So the centroid means that L over 2. So this slide show how to determine the magnitude of resultant force. So based on this figure, okay, we consider this is the distributed length. And then how to determine the force magnitude? This is the force magnitude dF. So dF is equal to dA. dA means that area under the distributed loading. So this is C is the centroid. A is the area under the loading. So this is the FR. And then this slide show locations of the resultant force. Means that after we calculate the magnitude, the FR, then we need to get what is the distance of the locations of the resultant force. So assuming that FR acts at X bar, it will produce the moment about point O. So let's say here, we want to calculate the moment here. So the moment here, moment resultant is equal to this one, this distance, X bar times FR. So we can get this one. We produce the moment. Okay, this slide also show us how to determine the location. So the locations of the resultant force. So it names is at X bar. So means that from the integration of this part, so XW dx divided by the WX. So or we can have the XdA divided by the dA. So this is only we only consider this small part. This one. So we can determine the location. Okay, now we go to the example 4.23. Determine the concentrated load. What is the concentrated load? Its common name is the resultant force or resultant distributed load. So for this example, we have beam here, and this beam is subjected to the UDL. So the intensity of the UDL W is given 400 pound per feet. So first, we need to determine the force resultant. So what is the magnitude? Now we want to determine the magnitude. So the magnitude is FR. So FR is determined by the area under the rectangular. For this case is the rectangular. So the area is the length is 10, and then the intensity is 400. So the area means that 10 times 400. So FR is given 400 times 10. So the magnitude is 4,000 pound. This one 4,000 pound. So after we determine the magnitude, we need to determine the location. Location of the FR. So how to determine the location of the FR? So we understood that force resultant acting centroid of the beam. So how to determine the centroid? So if we have 10 divided by 2 here. So the location X bar is equal to 10 divided by 2 is equal to 5. So that is why the locations of the force resultant is 5 feet from this beam. Understand? Okay. Let's move to example 4.23. Now determine the concentrated load or the force resultant. Okay, so what types of the loading here? So just now we study rectangular. So this one is triangular. So this is triangular shape. So now number 1, we need to determine the magnitude of the FR. So we know that the magnitude is the area under the loading. This is the area under the loading is triangle. So what is the area of triangular? Area of the triangular is half times length times W. So now W is 6. W is 600 Newton dot meter. This one. This is W. 6 is the length. Okay, so half. Half is the area of the triangle. So the magnitude of FR is 1,800 Newton. Okay, next, we need to determine the location. So, for the triangular, the location actually is, you can remember, the location is 1/3. 1/3 from the base. This is the base of the triangle. So let's say the length is 6. So 1/3 from 6 is 1/3 from 6 is 2. So when this is 2, when you measure from this point, so 6 minus 2 is 4. This 4 if you measure from this point. But if you want to remember, must remember, if we have triangular load like this, so the location of the FR is commonly at the 1/3 of the base. 1/3 of the base. Measure 1/3 of the base. Please note that the centroid of the right triangle is at a distance 1/3 the width of the triangle as measured from its base. Okay, next, example 4.24. the loading on the beam as shown. Determine equivalent force at its location from point A. So you can see here how many type of loading here. So this is the beam AB. So you have two type, right? So you can distribute into two type. So one part is triangle and one part is rectangle. So we need to determine the equivalent force at its location. So we need to determine what is the force resultant and the location from A. So number one, the distributed loading can be divided into two parts, one rectangular loading and one triangular. And then how to determine the force resultant. So this one here, we understood that the force resultant FR1 must acting here, right? Here is 1/3 from the base. And then FR2 is located central of this line. So this line is 8. So 8/2 is 4. This is 4. So this is the location. So how to determine the FR? FR is the area under the loading. So you need to determine the triangular area and the rectangular area. Can you do that? Yes, definitely yes, right? So this is for the FR1, R1, half times 150 times 6, so you get 450. So this is the location we already determined, right? This is from A, and then for the rectangular load, the FR2, 150 times 8 is 1200. This is the magnitude for the FR2. And the line of action, the location is 10 feet from A. Okay, this one. So this is FR1, this is the FR2. So the total for the force resultant is FR1 plus SR2 is equal to 1650 pounds. And then we want to determine the moment resultant from the point A. So here we need to resolve to point A, and then this one we need to resolve to point A. So here 450 times 4 plus 10 times 1200. So the total moment resultant is 13,800. So now this is the force resultant, the total force resultant acting like this. So we need to determine what is this distance, the location. So the location, since we know that the MRA here is force resultant times this X. So in order to determine the X, so we need to divide the 3,800 divided by the 1650. So we can determine that X bar is equal to 8.36 from point A. Now we move to the last example, 4.25. The loading on the beam as shown. Determine equivalent force and couple moment acting at point O. So here, what you should do? So what type of the loading? So you have two triangular load. So this is one part and this is another part. So we know that the locations of the FR must 1/3 from the base. So this one 1/3 from here. So this is the FR1, this is the FR2. So don't forget, this is the point load and this is the couple moment, 500 kN/meter. So in order to determine the force resultant, so we need to resolve the magnitude FR1 and FR2, and then we want to determine the location, right? So this is the FR1. FR1 half times 6 times 7.5. So the magnitude is 22.5. And then the location is 5 meter. Okay, because 2/3 over times 7.5. This is from O. And then the second one, we have FR2. Half times 6 times 4.5 is equal to 13.5. So the location is 9 meter from O. So this is the location for FR1. This is the location of FR2. Okay, now we need to combine the three forces. Okay, the total for force resultant is FR1 plus FR2 and then plus this point load 15. So the total is 15 kilonewton. So now we need to resolve the moment at point O here. So moment resultant at point O is equal to this one. Acting, we just take 500 because it's a free vector, plus this loading FR1 times 5 plus FR2 times 9, and the last one 15 times 12. So the total moment resultant is 914 kilonewton dot meter. Okay, that's all for today. Hope you can achieve the outcome of the lecture, which is number 1, you should be able to determine what is the force resultant. Number 2, what is the magnitude of the force resultant. And number 3, to determine the locations of the force resultant. See you for the next lecture. Bye.